On April 18, 1983, I visited the J. Paul Getty Museum at Malibu, California for the first time. The main purpose of my visit was to see the museum and its renowned art collections. As I was walking and videoing through the colonnades full of visitors, I was casually looking for potential earthquake vulnerability of museum structural features, including the parking garage supporting the large pool. Decorative vertical terracotta tiles propped up at the roof lines seemed potentially hazardous to the visitors during earthquakes. I walked into different galleries featuring decorative arts that included working large grandfather clocks, antique furniture, paneled rooms with chandeliers, porcelain vases placed on the top of tall cabinets held by wire. Antiquities were exhibited on ground floor galleries. Bronze statue of a young man and an intricate mythical sculpture in lucite case were prominently displayed. Marble heads supported on slim tall pedestals attached to metal base plates were lined up around an ancient mosaic floor. In an adjacent gallery, delicate vases of different geometry were housed in large glass showcases with glass shelves. The showcases supported on leveling feet looked vulnerable to sliding and rocking during earthquakes. Large ornate pottery with small bases seemed extremely vulnerable to earthquake-induced ground shaking. What I saw during my visit was shocking. It was clear that during a major earthquake, the museum and its collection would sustain a great deal of damage and irreparable loss. It was then that I was authorized to perform site-specific site studies to evaluate the seismic setting of the museum and assess credible response of the museum's structures and art collections to seismic event with 225-year mean recurrence rate. Geoscientific studies indicated that active faults significant to the museum are Malibu Coast Santa Monica Fault and San Andreas Fault, each capable of inducing free field mean peak horizontal acceleration at the museum, respectively 0.7 and 0.2 Gs. Principal horizontal component of developed time history of maximum expectable earthquake at Malibu indicated that during 20 seconds of strong motion, peak-to-peak ground displacements at the museum could exceed 22 inches. Off-the-shelf, low-amplitude, high-frequency, steady-state vibration isolators such as elastomeric and rubber pads, air cushions, coil springs, and a combination of the two were useless and could not dissipate the expected random high ground accelerations and large displacement at the museum site. A ball transfer would meet that requirement. In response to earthquake-induced floor shaking, the ball rolls on the surface of the floor and prevents horizontal component of the motion from being transferred to the art object. Flat springs dissipate the vertical component of the floor vibration. To demonstrate museum's art collection's response to earthquakes, I made a portable small single degree of freedom shake table to demonstrate the response of model art objects on vibrating floors. Approximate replicas of most vulnerable objects placed on the shake table showed how in few seconds of shaking the models become unstable and topple. Also shown was vulnerability of restored objects anchored to floors that break at repair joints during ground shaking. To demonstrate the effectiveness of delinking to prevent ground shaking from being transferred to the object, a top-heavy tall model supported on ball transfer was subjected to shaking. The model did not fall during strong shaking. However, it did wander around on a shake table that demonstrated the need for a mechanism to maintain the object in its original position during the entire shaking period. I devised a centering system consisting of a bowl, a telescoping coil spring-loaded ball transfer that retained the object in its original position. The combined single device concurrently reduced the ground acceleration and displacement at the same time, a system that had never been devised before. In order to verify the efficiency of the system, a full-size replica of Getty Showcase was tested on an industrial shake table. Hydraulically driven triaxial table vibrated along two horizontal and vertical axes. To evaluate the efficiency of ball transfers, two full-size pedestals each supporting a brittle object, the left with ball transfers and the other without ball transfers, were subjected to shaking. The wooden replica of the Getty showcases included a glass shelf and a cut-off observation window to record the behavior of the objects on the shelf during the shaking. The replica was subjected to incremental levels of earthquake shaking with and without isolator. This is the side view of front to back shaking without the isolator. The replica showcase without isolator was tested predominantly shaking side to side. 4 ball transfers attached to the showcase reduced the friction between the platform and the showcase that prevented the shaking to be transmitted to the showcase. Centering mechanism returned the case to its original position while providing damping by gravity and rolling friction. The front view of isolated replica showcase with loose plates on the glass shelf subjected to different levels of shaking. The bar attached to the platform shows the relative amplitude of platform shaking along 3 axes and showcases response to the shaking. This is the side view of isolated replica showcases subjected to different levels of shaking. Testing manager John Stossel summarizes the result of the shake test and efficiency of the tested isolation system.
What we're looking at here is our 2-channel analyzer, which is monitoring the accelerometer on our shake table, so we can see what the motion of the table is when we're shaking the cabinet. As you can see, we have a peak of about 1.5 Gs going into the table in the horizontal direction. As the earthquake dies down, the signal is reducing. That's effectively the end of the earthquake. This time we'll be looking at the response of the cabinet shelf, top shelf, to the same earthquake, same level. And we'll be watching that here on the screen. Now we see there's the earthquake coming in, there's the shelf responding. Of course, it's much less than the table motion because of the effect of the rollers on the cabinet isolating the horizontal motion of the table from the cabinet. Now we will look at the response, frequency response of the table motion and the cabinet motion and the transfer function between the two, which is an indication of the effectiveness of the isolation system of the cabinet. This is an example of the frequency content of the earthquake from 0 to 25 hertz. We can see most of the energy is in the 1 to 3 hertz range, and it significantly drops off. Now if we look at the cabinet response, the upper shelf response, we see that there is very little frequency content from 0 to 5-10 hertz. Now we can also look at the transfer function between the accelerometer on the shake table and the accelerometer in the cabinet in the horizontal direction, and this will give us some indication of the effectiveness of the isolation system. We can see that there is a peak at a very low frequency, approximately 0.6 of a hertz. This is most likely the resonant frequency of the isolation system, the casters in the dish with the springs mechanism on them. Very low frequency, very lowly frequency tuned system. Now as we move out, we see that the transfer function is very small, less than 0.1 between those two accelerometers. This shows that the isolation system is very efficient through this frequency range. And it isn't until we get out to about 14 hertz, 13, 14 hertz, that we start to see the transfer function pick up at the higher frequencies.
Factory frames of glass showcases were fabricated using light profiles inadequate for directly connecting the isolators to the showcases that required designing separate structural frames on which to mount the heavy glass showcases. An exploded perspective drawing was prepared to show the manner in which the showcase would be attached to the structural frame and isolation system. The dimensional precision being critical, full-scale wooden models of the showcase frame, the structural frame, and isolation elements were made to demonstrate the sequences in which different pieces would be assembled. Based on Quantex Systems fabrication drawings and full-scale models of the structural frame, Getty commenced in-house fabrication of steel framing and isolation elements for their showcases. In February 23, 1988, U.S. Patent 4726161 was granted for inventing the concept and design of earthquake isolating support. Another earthquake isolation concept that I presented to Getty included isolating entire gallery floors that would delink a large number of exhibited objects during ground shaking. One of the main advantages of delinking floors is substantial cost savings compared to isolating individual works of art.